Let's consider the statue and consider the forces on it. We have a tension from the rope or the cable. We have its weight, and because it's submerged in a fluid, whether it's air or liquid, it's going to have some buoyant force B on it, where the buoyant force is going to be the weight of the displaced fluid when this object is submerged in. So the volume of the statue is going to be the mass of the statue divided by the density of the statue, which is in this case gold. So we get 15 kilograms divided by 19.3 times 10 to the third kilograms per meters cubed, which is a value we would read from a table. And this would give us about 7.77 times 10 to the minus 4 cubic meter. And now for the buoyant force in the water, that would be the weight of the displaced water, which is going to be the mass of the water times G. And the mass of the water is the density of water times the volume of the displaced water, which would be exactly the same as the volume of the statue, times G. And these are values we know. The density of water, that is still, is 1.3 times 10 to the third kilograms per meters cubed. The volume is 7.77 times 10 to the minus 4 cubic meter, and G is 9.8 meters per second squared. Notice that cubic meters cancel, leaving us with kilogram meters per second squared, which is in Newton, and this gives us about 7.84 newtons. Since the statue is at rest, then we know that it's in equilibrium, which means that the sum of the forces in the y direction has to equal 0, which means that the tension plus the buoyant force in water minus the weight of the statue has to equal 0, so that the tension itself is going to be the weight minus the buoyant force in water, and this equals 15 kilograms times 9.8 meters per second squared minus the 7.84 newtons. And if we do this, we get about 139 newtons, considering significant figures, where the mass times the acceleration due to gravity is about 147 newtons. So if we consider now the statue to be in air, then the buoyant force in air is going to be the density of air times the volume displaced times G. And the volume of the density of air is 1.2 kilograms per meters cubed. The volume is still 7.77 times 10 to the minus 4 cubic meter, and G is 9.8 meters per second squared. This gives us 9.1 times 10 to the negative 1/3 Newton. And as we did before, if we look at the tension now at rest for, it will be the 147 minus the buoyant force in air, which is 9.1 times 10 to the minus 3 newtons, which is going to be approximately 147, because this is 0.0091, so it's for all significant figures would be 147 newtons. So in air, the buoyant force is almost negligible because the density of air is so small.